Okay, so this way figured out like this. So this is a formula we have derived yesterday, okay? Average value of spin. Okay, I will tell you something. So if we are in the quantum domain, okay? Let's say you are quantizing your electric field, electromagnetic field, then these A's and A stars will become actually, so A will become the annihilation operator for the electromagnetic mode, and A star will become the creation operator for, so it will become actually the A dagger, A star will become A dagger, and A will become A, okay? Got me? If we try to quantize, but okay, so we are not doing that thing here, so we are just in the classical domain. It was just to mention a point. So even if I try to calculate, let's say the energy, we will see in a moment, there will be, we'll see the energy contribution is from the two terms coming up, from this kind of term and this kind of term. We'll see it in a moment. Okay. Now, what are the values of this lambda? Now, let's look at this thing. So, since we are taking the circular polarization, is it? We are trying to calculate what is the average value of the helicity, okay, or what is the helicity of the circularly polarized wave, okay? Clear? So, what are the values of this lambda? So, lambda is actually plus minus, is it? Plus minus 1, okay? Plus 1 or minus 1, okay. So now let's look. So you are having this cross product. Let's check all, how many possibilities are. So lambda prime can go plus and minus, and lambda can go plus and minus. So how many possibilities are there? So you will be having, let's say, epsilon star cross of epsilon plus, okay, epsilon star minus cross of epsilon plus. You will be having then epsilon star plus cross of epsilon minus, okay, epsilon star minus cross of epsilon minus. Is it? So we are having these four possibilities. Now let's check out of these four possibilities how many will contribute, okay? So if you sum over, let's say, lambda and lambda prime, how many terms you will get? Actually 4 terms. So that means 1 term, 2nd term, 3rd term and 4th term. And those actually total you will be having 8 terms. Got my point? Okay. So rather we will be getting 16 terms. 4 terms from here, 4 terms from here, is it? So those are all 8 terms. Okay. So now let's check what is the value of this thing. Okay. So if you remember, epsilon, if you are in unit vectors, E1, anybody remembers how we wrote epsilon? In terms of linear polarization, E epsilon plus minus. So it's E1 plus minus I, E2 by root 2. Is that true? You remember it? Huh? So was this the notation? So we wrote actually epsilon 1 instead of E1. We wrote it like this: epsilon plus minus I, epsilon 2. Okay? Remember it? You know it? So what is the epsilon 1 and epsilon 2? These are actually the linear polarization vectors. Okay? So you can think, let's say, okay, what is this thing? Epsilon 1 cross of epsilon 2, anybody? Cross product, what it will give me? So it will give me a third vector which is perpendicular to it. What will be that? That's actually the direction of propagation of the wave, is it? So let's call, how much is that? Anybody? How many? When is it? So how much is that? C K by omega. You remember it? That's equal to this unit vector n. Okay, so if you are having n is the direction of the propagation of the wave, so that's actually k vector represents the direction of the propagation of wave. So epsilon 1 and epsilon 2 are actually two linear polarizations. If you take their cross product, let's say you are having polarization along x-axis, then polarization along y-axis. If you rotate them, what you will get? You will get z-axis. Is that true? So that is this kind of object. Clear? So now let's take these kind of products. Let's evaluate these products. Okay? So you are having epsilon 1 plus I epsilon 2 by root of 2 cross of epsilon 1. Okay? So it's epsilon plus I epsilon 2 by root of 2. Okay? How much is that? Now epsilon 1. Okay. Now tell me epsilon 1 cross of epsilon 1 is? What is the cross product of a vector with itself? It is 0. Okay, what is, since epsilon 1 and epsilon, they are linearly polarized. Okay, so you are having epsilon 1 cross of epsilon 2, that's equal to, sorry, and epsilon 2 cross of epsilon 2, that's equal to 0. Okay, so now tell me what this epsilon cross epsilon, it is 0, epsilon 2 cross epsilon 2 is 0. What you are having? Epsilon 1 cross of epsilon 2, what is, how much is that? In, is it? So it is n. So you will be getting 1 as n. And plus, then you are having this I epsilon 2 cross. So you are having minus n. Sorry. Yes? So how much is it? Is equal to 0. Okay? Yeah, it has to be equal to 0. So now let's take this object. Let's take this object. Okay? So we are calculating how many possibilities. So the possibilities are lambda. Okay? You got my point? So let's try to calculate those possibilities. I think they should not be equal to 0. Oh, sorry, it is epsilon star. Oh, it's epsilon star. So it's how much is it? It's minus I here. So that's how much? So it is twice in. Twice in by root of 2. Not root of 2, it is 2. Because root 2, so it is simply I. Clear? Okay, now let's calculate this one. Epsilon star, so this will be equal to 0. This object will be equal to 0. And this object will be equal to minus in. In the same fashion. Clear? So tell me how many terms are contributing in the sum. So if I sum over lambda and lambda prime, how many? What I will get? So I will be getting the terms for when you are having lambda and lambda prime are plus pulses, or lambda and lambda prime are minus. Okay, in this very sum. So let's substitute these things, and we can use this epsilon plus and star multiplied by epsilon plus as in. Let's use those things. So what we will get? So we will use it here. So I'll be getting. So this is equal to twice 1 divided by 4 pi integral d3 k divided by 2 pi cube. Okay, omega by c. Clear? And then what you are having? So you are having in. So you are having in coming from each term. Okay. Clear? So what is in? Like this mod of, so it will be a star plus a plus k. So another term comes with a minus sign. Okay, so that's why you have a star minus k minus k. How much is n? Ck by omega, is it? So this n is equal to how much? So n is, yes, Ck by, okay. So now if you use n is equal to Ck by omega, omega and omega cancel, c and c cancels. So what remains there? Only k vector. I think there should be c. Oh, so there is no c here outside. I'm sorry, there is no c. Everybody followed it, what I have done? First tell me. Have you followed it? Okay, good. So, how much is it? It is 1 by 2 pi integral d3k divided by 2 pi cube. Okay? So, then you are having a vector k. Okay? So is I there? So we need to check, but I should not be actually there. So some I has बाहर एक I था? Yes, yes, there is an I when we take the derivative, is it? So that was minus I. So you are having minus I that. So it will become plus. Yes, great, good. So it is mod of a plus b square minus mod of a square. Now tell me what this a plus square gives me. Okay, look carefully. Look carefully. So what is a plus? It's plus means it's which? It's a wave which is actually the right circular polarized, is it? So plus gives me the right circular polarization. Minus gives me what? Left circular polarization. Okay. So now look here. So you are having a wave. K is a propagation, a direction of the propagation, is it? Or you can think it is the momentum along the direction of the propagation. Now look here. You are having for this very wave momentum. So since there is a plus sign here, is it? So momentum and the it is in the same direction. So okay, so you are having, let's say, right circular polarized wave. It goes along in the same direction as what is the momentum, is it? You got my point. So a plus. So this is actually the amplitude square. If you see, it is simply the amplitude square, and you see actually this kind of wave moves in the same direction as the wave, is it? So I call it as, okay. So what is the number here? +1, is it? So we call this wave is having a helicity of +1 because it moves in the same direction as the wave vector. Clear? Now in this case you are having a sign change. So that means this is a wave which moves in the opposite direction to the. So this is actually left circular polarization. Okay. So in other words, if you think of the rotation, since it is simply the angular momentum we are calculating or the spin angular momentum we are calculating. So you can think the angular momentum which you are measuring in the same direction as the momentum gives you the positive helicity. Okay, in other words, we call this right circular polarized wave is having a positive helicity. Okay, how much is that? What is the amount of helicity present? It's +1. If I let me take, if I take the projection of this very object along the direction of the wave, let's say projection means, so you take the dot product with this thing, huh? So let's say k dot k, that is, let's call that as 1, that's a number purely, is it? So like this thing, if I take the projection, okay, let's say if you are having a vector b and you want to take the projection along the vector a, let's say you take the dot product with a and divide by the magnitude of a. Clear? Got my point? So now let's take the projection of this very part along the direction of the wave vector. Okay, so what you will get? So you will get actually n dot k, let's say. So since n is the direction, since it is the propagation direction, so let's take n dot k divided by magnitude of k. Is it okay? So how much is that? So it is multiplied actually a plus k square. So much of this complete part. So in the direction of the propagation, how much you will get? So this is actually equal to 1, is it? So n is a unit vector. What is n dot k? It will be simply k. K divided by its magnitude is 1. So it's simply a plus 1, a plus k whole square. Okay? Magnitude square. Okay, so what you got? So this is actually the projection of the momentum along the direction of the propagation, is it? We call that projection as the helicity. Got my point? Now look at this very part. So what you get? So you get actually minus 1. Oh, samajh aa? So you are having there, so you are having, this is the term minus k mod of a minus k mod square. So you take its projection along the direction of the propagation. So it is like this, magnitude of k. So you'll get, so okay, so you are having, okay, so what you get? So you get minus a minus k square. Okay, clear? So that means you get how the amount of helicity minus 1. So in other words, this represents your right circular polarization wave, and this represents this left circular polarization. Right circular polarization is accompanied by positive helicity, and left circular polarization is negative helicity. Got my point? Samajh aa? Okay. So this is the spin angular. So the spin angular momentum here is simply the helicity of the wave. Okay, clear? Samajh aa? So you can think, okay, have you seen those ribbons moving like this? So how you see it? You have seen those Mobius strips, ribbons na tamasa. So curved ribbons, plastic. So how they move? So if you put, let's say, if you rotate it, how you will see it? So you will see the wave going like this way, is it? So, but if the person is, let's say, if you rotate it this way, how you will see the wave going? In the opposite direction. You can think this very wave, okay? So it's actually the right circular polarized wave, and it carries actually the helicity of plus 1. Okay, the positive helicity. The magnitude of the helicity is plus 1. And if you look at the opposite way, that's actually the left circular wave or circular polarized, and it carries how much? Minus 1. Okay, so it's not only true for these circular polarized waves. So if you are having plane polarized wave, it also carries how much helicity? Plus 1 or minus 1. Okay, or if you are having elliptical, so you are having only 2 helicities possible for a photon. Okay, so these are actually 2 physical degrees of freedom of the photon. Samajh aa? So that's why you in nature you observe only 2 types of these polarizations. Okay, you either left or right. Okay, plane up or plane down. Okay, so 2 types of polarization always. So in other words, the Hilbert space or the vector space is a 2-dimensional for a photon. It's a 2-dimensional vector space. Clear? Got it? Okay. So now let's take for, okay, similarly if you try to calculate the energy, let's calculate the energy. Okay, so let's calculate energy. So we will calculate the average of the energy. How much is that? So energy in an electromagnetic field, so this is the average energy. So it is simply E square plus B square. Since for EM field, E and B are same, so you write it as 4 pi integral d3 of x E square. Okay? Got it? Okay. So now what is your E? So E is equal to minus partial A by partial T, okay, 1 by C. So that's minus 1 by C. I can write simply A dot. Okay? Clear? So you know the form of A, is it? So this, so it implies, so you will be getting simply 1 by 4 pi C square integral d3 of x, average value of A dot square. So you need to, you know what is the formula for A dot? So you have to take it like this way, 1 by 4 pi C square, okay, d3 of x, average. First you take A dot product with A dot. So you know what is the formula for A dot, is it? Yesterday we have calculated, is it? And take the dot product with itself. So you differentiate between dummy variables, okay? You put one as omega and k, another as omega prime, k prime, then put a dot product, clear? So this will be the home assignment to calculate. So the energy will turn out to be, so the average energy will be simply, okay, 1 by 2 pi d3k divided by 2 pi cube, okay, omega a plus a mod square plus a minus a mod square. Okay, got it? So now, so both helicities are contributing the energy. So this is the amount of energy due to the right circular polarized wave, and this is the energy due to left circular polarized wave. So this is, here it is home assignment. It's very simple, trivial. Okay. So yesterday I have done it actually. So you just need a little bit interchange. So we had a cross product in the earlier calculation. Now here it will be actually a dot product between those polarization vectors. Okay. So and you have to carefully do the dot product. Okay. So that means, okay, now tell me what is the amount of energy associated with a let's say plus mode, let's say plus polarization. It's omega, is it? Otisha, omega divided by 2 pi. This is the amount of energy. So let's say if you are having, okay, let's say if you are having okay, so for a given mode, let's say for a given mode, lambda and k. Okay, let's take you are having a wave. Okay, you take one, let's say, oscillation or one mode. Okay, specified by some polarization lambda. Okay, so lambda can be plus 1 or minus 1, and in wave vector k. So this is the momentum. So what will be the average spin? So in this very case, so for lambda and k, anybody? So what was our average spin? So it was 1 by 2 pi integral dash dash dash. Then you are having k, okay, a plus k square, is it? So this is for plus k. In other case, it is minus k, is it? So I will write it like this thing. So lambda 1 divided by 2 pi, okay, k. So you are having a lambda k mod square. Is it true? So what is lambda? So lambda can be plus minus 1. Is it okay? So look here. So what is the average value of the spin? Let's say if you are having a polarization state plus and wave vector k, so it will be plus, okay, plus 1. So it will be simply k by 2 pi a lambda a plus square. So it is this very term. So you can be having, let's say, lambda equal to minus 1. It will be the other term. So you got it? So this is the amount of polarized. So this is the average value of the spin in a mode defined by lambda and k. Let's say polarization lambda and some wave vector k. So we can write it in this fashion. Okay, got it? So look in this very formula. So you are having this k as a minus k, let's say. So this is, okay, so you are having 1 by 2 pi sitting outside. So k, a plus k. So this thing, so because this is actually the average value of the spin, so in plus mode defined by wave vector k. Okay, everybody followed it? Okay. So similarly, I can calculate what is the amount of energy. So in lambda k for each mode, how much energy is present in each mode? So how much is that? So it will be since both the terms are positive, is it? So this is positive and this is also a positive quantity. Okay. So how much is that? So it is simply omega divided by 2 pi mod of a lambda k square. Clear? So now check the relation between the two. Okay. So let's calculate the relation between this thing. So you can write it in, or I can write this epsilon lambda k. Okay. So it is equal to some lambda. Okay. So Anybody? Can you? What is that? So it is lambda omega. Okay, let's write sigma. Let's write sigma. Shall I? Okay, so anybody? What is the sigma? Tell me. Sigma, I will write. Okay, so let me write it this way. So let me write lambda omega sigma. So it is magnitude of K divided by pi. So what I need to define one more quantity. So what is the relation between the two? Huh? Okay, so let me define a quantity. Okay. Define a quantity sigma known as helicity. Let's write separately, known as helicity. How we define it? Sigma is simply, it will give you how much values? Plus minus 1. Okay, so let's define it. So it will be simply magnitude of K divided by 2 pi A lambda square, okay, multiplied by, okay, so let's define this as helicity. Okay, so what is the relation between the two now? Now let's put this epsilon in terms of sigma. So which gives me this K lambda, so it's simply equal to lambda omega sigma. Yes. I think we have missed a C, factor of C somewhere. Somewhere we have missed a factor of C. Okay, so you need to check. So this will be actually the relation between helicity and the energy. I want to see it like this thing. Okay, so there is a, we don't need to do this thing here, but I want to relate it to the quantum mechanics. Okay, so what is the value of lambda? Okay, so sigma is helicity, is it? Okay, so I can write lambda into, okay, so I can write this energy. So on the left hand side, I am having actually energy, okay? So this energy is equal to plus minus helicity. Is it true? Multiplied how much? So let's not write plus minus. Helicity multiplied by omega, okay? So lambda can be plus minus 1, okay? So it's actually lambda times sigma. So you can call it as a, okay, sorry. So it is simply omega sigma, I'm sorry. So you are having helicity multiplied by how much? Omega, is that true? So is this the relation? Okay, so it is in the classical electrodynamics we are having. So if you know the helicity, you know the energy of the mode. So you, okay, you know the frequency of the mode, you can write what is the energy, is it? So how much helicity you are having for a wave? Plus minus 1, is it? Okay, so now let's look at the quantum mechanics. So what you are having energy? H cross omega. So what are the units of this H cross? Joule second, is it? So how, that are actually the units of the angular momentum. Is it true? So that means if I make a transition from the classical electrodynamics to the quantum electrodynamics, or from the classical physics to the quantum physics, so this helicity will become actually, since this H cross is actually the unit of angular momentum, this helicity will become actually the spin of the photon. Okay? So how much units will be you are having? Plus minus H cross. So helicity, whether you define it in terms of the classical electromagnetic theory or in the quantum mechanics, you will be having the same values, same values, plus minus 1. So you will be having corresponding to two helical states, you will be having two spin states. Although photon is a spin 1 particle, okay? But in nature you realize only two possible states. Okay, so those are, you don't call it as an up and down spin. So you call it simply plus helical state and the negative helical state. Okay? So samajh aao? Got my point? So this is actually the transition from, let's say, the classical to the quantum domain. Okay? So do you feel there is actually the relation? Are they analogs to each other? Got my point? So that means the amount of angular momentum that's carried by a photon is h cross. Okay? Okay. So this is all about the superposition of the waves. Okay, so let's take something new. So the superposition of the waves, what we have done here, so it's simply the Fourier decomposition. So you are tired? Oh, you feel tired, you are yawning there. So what is the reason? So you have not slept well? Huh? So you have come, I mean, yes? Okay. Summation of lambda, so epsilon lambda a lambda a e raised power I a dot r minus omega t plus complex conjugate of the first term. Okay, now look here, it is simply the Fourier decomposition into the modes. So you are summing over now, so you are taking a of xt, you are decomposing it into the Fourier modes. This is a simple decomposition of a time dependent field. Okay, Fourier decomposition of the time dependent field A. Okay, so corresponding to each mode you are having this exponential factor. So as a wave, is it? So because you are having each mode defined by k and omega. Okay, and with the polarization lambda. So samajh. So how you define the Fourier series? How you define the Fourier sum? You expand a given function. So in terms of the fundamental modes, is it? Is that true? Or in terms of the individual modes, and you sum over the infinite series. That is the same thing here. Okay? So and we have seen this is actually the transverse in nature. Okay? Okay, in the radiation gauge, we are having the transversality condition. What is that? K dot E for each mode. So this is very important. Each mode is actually perpendicular or orthogonal to the direction of propagation. Okay? Got it? So this is very important thing. Now if I take the electrostatic field, so this is electromagnetic field. Okay? So this is the time dependent case. Now let's take the electrostatic field. When I take the electrostatic case, it's actually longitudinal in nature. Okay? Because it is a static field. So what is the point, if you take a point charge, how you define the electric field? So these are the, I mean you can think the electric lines of force radially coming outwards, is it? So that means the direction of the electric field and the propagation of those, I mean so they are along the same direction, is it? So in that way you call it as a, what? Longitudinal wave. Okay? So let's take the electrostatic field and figure out what is its Fourier decomposition. Okay? So you have done the Fourier transforms, is it? So let's calculate the Fourier transform of this Coulomb potential 1 by r. Okay? So you do it by the formula. So how we define, now anybody tell me? So you are having this F tilde k. So you write it d3 of r divided by, okay, what is the factor? 2 pi, how much is the root of it? Like this thing, okay, then you are having f of x e raised to minus I k dot, is it? Or let's say f of r k dot r. So this is the formula you know, okay? So take this f of r to be 1 divided by r. So samajh aa? And try to figure out, you will see the doing it this way, so it will diverge, so it will become infinity, okay? So you need to actually use instead you use f of r e raised power minus alpha r divided by r. You cover potential and then put alpha equal to 0. So this is the assignment for you people. Whoever is not able to do it, just look at the RFK. It's given in RFK. Okay. Okay. So this is the but we will do it in a different way. So you know this kind of formula, calculating the Fourier transforms. So this is a very important problem. So if you take the Coulomb, if you take simply the Coulomb potential 1 by r and try to calculate what is the Fourier transform related to 1 by r, so you will see the integral will actually diverge. Okay, so it's because the long range nature of this Coulomb potential. Okay, so but instead what you do, you put a cutoff. Okay, e raised power minus alpha r, you multiply it by this thing, so that means there is a range for this very potential. Okay, so calculate the Fourier transform for this thing. It is okay convergent integral, and you will get the value. Is it? At the end you put alpha equal to 0. So you will be getting actually then this f tilde of k, you will be getting actually proportional to 1 by k square. Okay, so you got my point. So this is the the Fourier transform of this Coulomb potential. Okay. Okay, so now let's take it the other way around. So let's start. Okay. So in other words, it is the Fourier decomposition of the electrostatic field. Okay. So we have. So let's consider a point charge. So you are having a point charge Q. So what is the charge density? So it's simply equal to Q. Okay. Located at origin. So this is the charge density. So I can write the Poisson equation. Okay. So nebula square phi. So that's equal to minus 4 pi rho. So how much is that? Minus 4 pi Q delta 3 r. So I will not explain these things, sir. These things we have been doing for for a longer period. Okay, so now let's take the Fourier transform of this phi. Okay, this phi of r. So what is that? Anybody? So it is integral d3k divided by 2 pi cube. So I will use this. Don't use root here. So I will use the symmetric constant 2 pi cube. Okay. So it will be some. Let's say phi of k e raised for I k dot. Okay. So this is the Fourier transform. Now look here. So this is a static case. So that means so you don't have actually the time dependence in this Fourier transform. Clear? So you don't have actually omega here, omega t. Samajh? Okay. So what is the delta 3r? Okay. So it is d3k by 2 pi cube. Okay. E raised for I k dot. So substitute it in this very equation. Let's call this as equation 1. Okay. So what I am having? So nebula square acting on this d3k by 2 pi cube. So it is now a simple thing. So phi of k e raised for I k dot r, that's equal to minus 4 pi q integral d3k divided by 2 pi q e raised for I k dot. Okay. So now let's apply this nebula square on this thing. You will be getting I k square. So it's like this thing. d3k divided by 2 pi cube. I will take this on both sides. So you will be having. So when you differentiate it twice, so it is simply minus k square. Okay. So then you are having this phi of k. Okay. So you take this on this side. So it's 4 pi q. Okay. E raised for I k dot r. So that's equal to 0. So it means this objective has to be equal to 0. So I am going quickly because I have shown these things already. Okay. How to do these things. So which implies. So what is phi of k? So it's actually the Fourier transform. So this is the Fourier transform of this phi of r, is it? Okay. So you are having this phi of k as 4 pi q divided by q square. What I was saying earlier. So this is the Fourier transform of the Coulomb potential. Okay. So now let's try to calculate the electric field. So then we can see actually the nature of the electric field. So you are having this electric field, it's equal to minus nebula phi. Is it? Is it? Okay. So now let's take the Fourier transform. Okay, so let's write first. So minus nebula phi. What is phi? It is this object, is it? So let's try. So it is d3k divided by 2 pi cube. Okay. Phi of k e raised for I k dot r. Okay, so now let's act. So it will be simply d3k divided by 2 pi cube. So phi of k will be there. So gradient will act on this object. So you will get I k down e raised for I k dot r. Okay, let's call this as second. Okay. So now let's calculate. So let's try the Fourier transform of. So Fourier transform of electric field. So that will be simply equal to d3k, okay, by 2 pi cube. So let's write G to be the Fourier transform of this electric field, okay. So it will be e raised to. So this is simply the definition. So this equation is the definition of the Fourier transform of the electric field, is it? So this is how we define the Fourier transform, okay. Okay. So let's compare second and third. So this is actually, I have calculated the Fourier transform of E from the Fourier transform of the potential, is it? So but from the definition, so this is the Fourier transform of the E. So now let's check it. How much is that? So G of k is simply, so which implies G of k is simply equal to minus I k phi of k. How much is phi of k? Phi of k is, okay, 4 pi cube. So it's minus 4 pi I q by k square, and you are having a vector k. Now G is actually, so this G is the electric field in the Fourier space, is it? Or in the momentum space. So this is the electric field in the R space, coordinate space. This is the electric field in where? Momentum space. Clear? So now look here. What is the direction of this electric field in momentum space? It is k, direction of the propagation vector, is it? So G and k are having the same direction. Clear? So if the k is it is the direction of the momentum. So in other words, the G has the same direction, is it? So what kind of waves we call them? Longitudinal. So this is the proof that a static electric field is longitudinal in nature. Okay? So any question till now? So if you have any question, so how much? So we'll be doing Islamic. So let's take this topic.